Hi, my name is Tanner. I'm a geology master's student at Bowling Green State University, and today I'm going to be reacting to When It Rained for 2 Million Years Straight by the First Dot. So I think this is talking about the Carnian pluvial events, which I don't know too much about, so I'm really excited to see what they have to present here.
You're standing in this painted desert of Arizona. Red sandstone stretches to the horizon. The air is dry, sharp.
It's very pretty. So I think that video is at Big Bend.
Through layers of rust-colored stone laid down grain by grain in an ancient wasteland.
Is this AI generated? I'm not talking about the video, I'm talking about the voice.
And you'll hit something strange. A band of black shale. Dark, organic, waterlogged. Then below that, red sandstone again, just like the surface. That black layer is a scar. It marks the moment, 234 million years ago, when the driest parts of Earth became swamps for 2 million years straight. This is the story of how volcanic fissures rewrote the rules of climate, drowned an entire world, and accidentally handed the planet to the dinosaurs. 235 million years ago, Pangaea was a single landmass stretching from the...
Okay, that is a very bad depiction of Pangaea. I don't know why they're using that. There's so many better outlines of how Pangaea looked. This doesn't tell you much about any of the I guess paleo climatic conditions. You know, you'd have some desert areas and some wetter areas. You'd also have some mountain ranges. And with this just flat orange, you just don't get any of that context. So I kind of dislike that.
North Pole to the South Pole. No Atlantic Ocean. No Pacific separates Asia from the Americas. Just one enormous continent surrounded by a single enormous ocean called Panthalassa. The interior of Pangaea, thousands of kilometers from any coastline, baked under relentless sun.
Yeah, okay, so one thing that's one thing that's really interesting about Pangaea, because of how, exactly how it was set up, kind of like a sea, almost, it could, during that time, could have been the largest desert in all of, Earth's history. Because when you have, as much, right next to the equator, or, in really warm zones, as you do, or with sometimes during Pangaea's existence, you just end up with these absolutely massive, giant deserts because of how the continents are assembled. And it could have been, we don't know too much about super early Earth, but it could have been the largest desert Earth has ever seen. So I always find that really crazy. And I think that this is a very interesting thing to talk about, especially getting into climate and why some areas are wetter than others. Very cool.
Surrounded by a single enormous ocean called Panthalassa. The interior of Pangaea, thousands of kilometers from any coastline, baked under relentless sun.
Yeah, I think the carbon dioxide was also higher then too.
Temperatures ran several degrees hotter than today.
Yeah.
Rain came in seasonal bursts called mega monsoons, but between...
Okay, so when he's talking about rain coming in bursts and mega monsoons, what he is talking about is, think of climates that are closer to the equator that are seasonal, where you have a wet season and a dry season. Whenever you have those wet seasons, you have a huge downpour. Those are going to be huge monsoons, typhoons, or hurricanes, as some people call them. Here he's talking about a seasonal climate.
In those pulses, the land dried out completely. Rivers existed, but most were ephemeral. They swelled during the wet season and vanished during the dry. The landscape looked like modern Arizona or central Australia. Red rock, scattered shrubs, occasional stands of trees near water. Deserts dominated. The flora had adapted accordingly. Seed ferns, extinct plants that produced seeds but resembled ferns, covered much of the undergrowth. Conifers, the ancestors of modern pines, formed forests where water persisted. Cycades, squat and palm-like with waxy leaves to minimize water loss, dotted the plains. The animals that thrived here were specialists. Dicynodonts, herbivores the size of cattle with barrel-shaped bodies, beaked snouts, and two prominent tusks, were the most successful large plant eaters on the planet. Plesarias, a North American species, traveled in herds and used its beak to slice through tough, fibrous vegetation. Rhynchosaurs, smaller herbivores with powerful jaws and teeth fused directly to the bone, fed on roots and tubers. Edosaurs, four-legged, heavily armored archosaurs covered in bony plates, looked like armored pigs and browsed on low-growing plants. Desmetosuchus reached 16 feet in length and had spikes jutting from its shoulders. The apex predators were Rauisuchians. These were not dinosaurs, but a separate lineage of archosaurs that walked on four legs and could rear up on two. Postosuchus, built like a crocodile crossed with a tyrannosaur, hunted the herds of Dicynodonts. It was the top carnivore in a stable ecosystem that had persisted, with variations, for tens of millions of years. Dinosaurs existed. They were small, bipedal, and rare. They left a few fossils. They were nobodies. Around 234 million years ago, the western edge of Pangaea, in a region that would eventually drift north to become Western Canada and Alaska, began to split open. Fissures hundreds of kilometers long opened in...
Okay, yeah. So one thing that he's basically talking about here is the breaking up of Pangaea, and it's largely thought that when you're talking about things like tectonics and look over very long periods of Earth's history, one of the things that causes continual evolution and renewal of Earth's plates is this thing called the Wilson cycle. So this is called the supercontinent cycle, and I believe it every 700 to about every billion years you have a new supercontinent assemblage. The most recent is Pangaea, and I think right now we're in a mid Wilson cycle continent stage, so all the continents are distributed. But if you were to just imagine running into the future, like a couple 100 million years, maybe like 400, 500, it's not unlikely that you would get some of those continents starting to clump back together again. So one of the things he's talking about here is whenever you get a supercontinent, the thing that tends to break it up is what we like to call what we think of kind of like a mantle plume, which is basically in the deep earth there are different layers of compositions, and occasionally you get these new compositions upwell to the surface, and when they do, they cause a lot of stress on the surface crust. And if you have the upwelling being very continuous and prolonged over long periods of time, you can have continents like literally break apart and separate into different units. If you're really curious about this, I suggest looking up the East African Rift. This is where it's currently happening in Africa. A continent separation, not a supercontinent separation, so it's a little bit different, but basically the thought is that there's stuff coming, there's a plume of very strange material coming from maybe like the mantle, maybe the outer core, that is pushing apart some of the plates there.
In the crust. Magma welled up from the mantle and spread across the surface in floods of basaltic lava. In some places, the lava piled thousands of meters deep. The eruptions covered millions of square kilometers and continued on and off for hundreds of thousands of years. The lava itself was a local catastrophe, but the gases it released were a global one. Magma contains dissolved volatiles, primarily carbon dioxide and sulfur dioxide, that erupt explosively into the atmosphere when pressure drops.
Yeah, so one thing that he's not talking about here, but is very important to understand kind of like what this entails, is like whenever you have a dumping of carbon dioxide into the atmosphere, this almost always makes the oceans more acidic and almost always makes the earth hotter. So, I mean, I imagine that's what he's going into when he's going to be talking about this event, but it just kind of like, I always think it's really cool to think about how, the earth is like a huge feedback loop, and even like deep earth processes impact things that we deal with every day, like the climate. Like there's a natural amount of carbon dioxide that is taken in by like oceanic plates and by living like animals and plants, that ends up in the deep carbon cycle that is sucked into, gets stuck in the earth, or deeper parts that can get sucked into deeper parts of the earth that take it out of circulation. So the earth is constantly releasing carbon dioxide and then sequestering it, and it's really cool.
The Wrangellia eruptions pumped billions of tons of CO2 into the air. Atmospheric CO2 concentrations, already higher than today, spiked further. Carbon dioxide is a greenhouse gas. It allows visible light from the sun to pass through the atmosphere and warm the Earth's surface. When that surface tries to radiate heat back into space as infrared radiation, CO2 molecules absorb it and re-radiate it in all directions, including back toward the ground. This is the greenhouse effect. It's natural and necessary. Without it, Earth would be a frozen ball. But the Wrangellia eruptions overloaded the system. Global temperatures rose by an estimated 4 to 7 degrees Celsius. That doesn't sound like much. It was enough. The oceans, which cover most of the planet's surface, began to heat up. Warmer water evaporates faster than cool water. The superheated surface of the Panthelastic Ocean started pumping water vapor into the atmosphere at an accelerating rate. Water vapor is itself a greenhouse gas, so this created a feedback loop. More heat, more evaporation, more heat. The atmosphere became saturated with moisture. The hydrological cycle, the movement of water from ocean to air to land and back, went into overdrive. All that water had to come back down. The warming didn't happen overnight, but in geological terms, it was sudden. Within tens of thousands of years, the climate system of Pangaea began to shift. The seasonal
Yeah, I don't know if that's actually true because, yeah, 10,000 years is very short. I would have to read a paper on that, but I feel like that's usually like the climate changes like that. They rarely happen in periods of 10,000 years. Like the only times I can really think of that is like what we're doing right now with the climate and also like the Cenozoic hyperthermals. So maybe that happened that way, but a lot of times it's usually just like a trend, like maybe for like 100,000 years or like a million years, you have like a constant amount of carbon dioxide that heats up the climate. So
monsoons,
I don't know if
which
that's
had been
true.
intense but predictable, started to change character. They became longer, heavier, more frequent. The dry seasons have shortened. Then they
Yeah, that is one thing that people don't really think about when it comes to things like climate change, is whenever you have more carbon dioxide in the atmosphere, this makes it so that the amount of heat that is trapped increases, and when you have more heat that is trapped, this makes storms and things like wildfires like much worse. So it's not just that like, oh, the sea level is going to rise. It's also or that the ocean is more acidic, but it's also that the natural disasters that used to be like not super strong become much stronger. The wind speeds become faster, the amount of precipitation, at least in certain areas, increases a lot, the amount of dryness in certain areas increases a lot. It pushes the extremes of the climate system in multiple dimensions. That's kind of like, at least whenever he's talking about the lead up to this 2 million year reign, that is like some of the like really important context and is almost important for understanding like modern day climate change.
disappeared. By around 234 million years ago, much of Pangaea had entered a new climate state. It rained, not in the sense of a single storm system, but as a persistent condition. The atmosphere held so much moisture that precipitation became near constant across vast regions. This was the Carnian pluvial episode. The rain fell for 2 million years, not continuously at every location, but as a planetary climate regime. Instead of distinct wet and dry seasons, the world experienced wet seasons and wetter seasons. River systems that had been seasonal became permanent and powerful. Erosion accelerated. Sediment, sand, silt, clay, washed off the land in torrents and poured into the surrounding ocean. The landscape began to drown. Red sandstone, the signature rock of arid environments, stopped forming. In its place, dark shales and siltstones accumulated in swamps and shallow lakes. Coal beds, formed from the compressed remains of waterlogged plants, began to appear in the rock record. In the oceans, the influx of sediment was so massive that it choked out the carbonate platforms,
It's a little
the Triassic
crinoid.
equivalent of coral reefs. These shallow water ecosystems, which had thrived by precipitating calcium carbonate from seawater, were buried under layers of mud. This shift is visible in the geological record on every continent. Below the Carnian pluvial layers, red rocks, evaporite deposits, fossils of arid adapted life. Within those layers, black shales, coal, amber.
Yeah, one thing that's fun about doing outcrop work like this, like whenever you're where this guy in the gray shirt is that a lot of times you can look at these vast like geologic events, these huge events like that were maybe global, the result of like global climate change. Then and you can like really just like stick your finger on that event as it is recorded in the rock record. So it's always like really, at least to me, it's like really magical to be able to think that like, oh, you had this crazy event that happened here, and that you can kind of like put your hand on it and see what happened after and see what happened before. You're presuming that everything deposited in a relatively continuous manner. So that is like one of the things that is very magical to me about a geologist. So it's very interesting to think about like why exactly you had this like huge like wet event, and especially he's talking also about the dirt flooding into carbonate platforms. So imagine places like the Bahamas today, that there used to be huge carbonate platforms, places like the Bahamas, and then it just rained so much, and in a lot of areas, like so much sediment that eroded from like mountains and places that usually wouldn't, because there's usually not enough precipitation to, that stuff washed out, went into the oceans. And one thing that's really specific about things that are like basically big coral reefs or big like rudous reefs, or things, or giant like carbonate banks, places where you imagine like corals and tropical fish. And that sort of stuff existing, that whenever you have a ton of just like mud, or like mud, just kind of like muddy water like sitting in there, it clogs up a lot of the things that like things like corals and those types of fish use to feed. So it basically just like stops that ecosystem in its tracks when you get a ton of like muddy water like that. So that's one thing he was talking about there. It's like, oh, you had this pulse, and then a lot of them just kind of died, which is terrible, but part of Earth's history.
Above them, red rocks again, but with a different cast of fossils.
Okay, yeah. What's really fun about like specifically this image, because I don't know if this is specifically that layer, but if it is, you can look at the like orangish rocks below that this specific like lateral event, like this like huge seam of coal, and then you can look at the red rocks above, and you can be like, oh wow, something changed. So you had one environment and then it shifted to another environment like very fast, because this isn't a super thick rock, and then it shifted back to the environment it was before. And that is always like really crazy, and usually has like really crazy implications for like how you interpret events like this throughout geologic past. And you can also think about like what that implies for what we were currently doing to the planet. It's very, very cool stuff. I love paleoclimate, and this is I'm exuberant about this because this is like one of my favorite subjects.
CPE left a global scar in the Earth's crust. The transformation of the landscape was total. The deserts of Pangea's interior became swamps. Ephemeral rivers became permanent waterways, carving deep channels through the bedrock. Floodplains expanded. Lakes formed in basins that had been dry for millions of years. The entire hydrological architecture of the continent changed. The fossil record shows this in fine detail. Pollen analysis, the study of fossilized pollen grains preserved in rock, reveals a dramatic shift in plant communities. Before the CPE, pollen from seed ferns dominates the samples. These were the plants of the arid world. As the rains began, their pollen disappeared. In its place, spores from ferns and pollen from conifers. Ferns thrive in wet environments. Conifers, with their deep root systems, could tolerate the waterlogged soils that were forming across the continent. The chemical signature of the CPE is equally clear. Carbon isotopes, different forms of carbon atoms that have slightly different weights, provide a fingerprint of the volcanic activity. The magma erupting from the Rangelia fissures had a specific isotopic composition. When that carbon entered the atmosphere as CO2 and was then incorporated into plants and marine organisms, it left a measurable signal. Geochemists can see this signal in rocks from around the world, a sharp negative excursion in the ratio of carbon-13 to carbon-12.
Okay, yeah, the way they're describing this, I don't know if I 100% agree with, because they're saying like this carbon is coming from a very specific place, and I don't know if they're usually able to do that. Maybe they are. But one thing that I know he's talking about that is true, and I'm like 100% sure is true, is that looking at carbon-12 versus carbon-13 is very useful when you're trying to figure out when there is a like mass die-off. It is basically like a huge extinction indicator. So one of the things that's really fun is being able to basically what they do is they look through a ton of material that has carbon in it, and they run it through a bunch of basically like isotope separators. So basically what they do is they have a giant device. I think that it has a magnet on it and it spins, and if something's heavier, it'll fly out further than something that's lighter. So I think it's like a spectrometer, but I'm not exactly sure because I haven't actually done that. But basically what they do is they atomize like material like this, stuff that we know is like from a certain age, and then they send it through, and then they get a ton of those data points, and then they try to put them with certain ages so that they can see how those isotopes change over time. And with those isotopes, one thing that's really interesting, specifically with carbon-12 and carbon-13, one of the things that they do is if you see higher amounts of carbon-12 depositing, usually this is or higher amounts of carbon-13 depositing compared to 12, like in a ratio. Usually this means that things are going well, the biosphere is pretty good, but sometimes what you see is that the amount of carbon-12 compared to the carbon-13, they spike or they get closer to equal, and when you see that spike in like carbon-12 compared to 13, if I remember correctly, that is usually associated with a big die-off, and that is because living things prefer carbon-12 to 13. So as long as things are alive, there's going to be a depositional mismatch. Like I believe your body does this. If you eat something and there's carbon-13 versus carbon-12, your body usually likes to get the carbon-13 out. So there is a disproportionate amount of carbon-13 in the environment than there is carbon-12, which is locked in our bodies. But when you have a lot of things die that has that carbon-12, then usually what you'll see is that all that carbon-12 that has been locked in like living things and recirculating through a lot of living things, it all splashes back into the environment. So you see a huge spike, at least in carbon-13 compared to carbon-12, that allows you to understand that there probably was a huge die-off or mass extinction event. So that's basically what he's talking about here. And I imagine what he's about to say is that when you see this huge die-off, that you're going to see a huge spike in this carbon-12 to carbon-13 ratio, and that this is partially indicated by this coal seam.
Marking the onset of the volcanic outgassing.
Yeah.
Oxygen isotopes, preserved in the shells of marine organisms, tell a similar story. The ratios indicate both rising sea surface temperatures and a massive influx of fresh water into the oceans. The rain was not just falling on land, it was altering the chemistry of the entire ocean. The amount of sediment washing into the sea was staggering. This is called the siliciclastic switch. Before the CPE, carbonate sediments, calcium carbonate precipitated by reef-building organisms, dominated the shallow marine environments. During the CPE, those organisms were overwhelmed by sand and mud washing off the continents. The seafloor was buried under layers of terrigenous sediment. Reefs collapsed. Marine ecosystems, the flora died first. Seed ferns, which had covered vast areas of Pangaea for tens of millions of years, were adapted to dry soils and seasonal water availability. The constant rain waterlogged the ground, roots rotted, seeds failed to germinate. Within a geologically short period, perhaps tens of thousands of years, seed fern communities collapsed across much of the continent. Conifers and ferns moved in to replace them. These plants had adaptations that allowed them to survive in wet conditions. Conifers with deep, oxygen-tolerant roots. Ferns with spores that could disperse quickly and colonize disturbed ground. The botanical landscape of Pangaea was transformed. The old, arid adapted flora was gone. For the herbivores that depended on that flora, this was a death sentence. Dicynodonts had evolved over millions of years to process tough, fibrous plants like seed ferns. Their beaked jaws, powerful neck muscles, and specialized teeth were optimized for that specific diet. When the seed ferns disappeared, the dicynodonts had no fallback. They couldn't efficiently digest the new vegetation. Populations crashed. Within the CPE layers, dicynodont fossils become rare. By the end of the episode, they were functionally extinct in most regions.
Yeah, so one thing I find that's crazy is because presuming that, I don't know if there are like any citations with the stuff, but presuming that that is true, and I know that at least people have done this before with things like dinosaurs, and other fauna, is basically that it's crazy how much they're able to find out just based off of like the changing morphology of different like creatures and dinosaurs, and what that allows them to understand about like the paleo environment, what it used to be like, and how faunal changes impacted like the ecology.
Rhynchosaurs suffered the same fate. Their fused teeth and jaw structure, perfect for slicing through roots and tubers, were useless in a world where those plants no longer grew. They went completely extinct. The collapse of the herbivore populations cascaded up the food chain. Rauisuchians, the apex predators, depended on herds of dicynodonts and other large herbivores for prey. When those herds vanished, Rauisuchian populations plummeted. They didn't go extinct immediately, but their dominance ended. The niches they had occupied for tens of millions of years were suddenly vacant. In the oceans, the extinction was equally severe. The burial of reef ecosystems under sediment destroyed habitat for countless marine species. Ammonoids, shelled cephalopods related to modern squid, experienced a major die-off, with many lineages
Okay, that is not a very good picture.
Or sea lilies, which filter feed from the seafloor, lost diversity as water clarity declined. Bivalves, which depend on stable sediment conditions,
yeah, so that's some stuff I was talking about earlier.
Of terrigenous material. The CPE was a filter. It didn't kill everything, but it selectively removed specialists, organisms that were finely tuned to specific environmental conditions or food sources. Generalists, species that could tolerate a wider range of conditions and diets, had a better chance. The survivors were the opportunists. Dinosaurs had existed for at least 10 million years before the CPE. They were small, rare, and ecologically marginal. The oldest fossils, from South America around 243 million years ago, belonged to bipedal carnivores, or omnivores, a meter or two long. Compared to Dicynodonts, Rauisuchians, and other dominant groups, their remains were sparse. The CPE changed that. In rocks from during and after the episode, dinosaur fossils become far more common, diverse, and larger. The extinction of Dicynodonts and Rhynchosaurs left an ecological vacuum, and dinosaurs, once generalist survivors, began to specialize and expand. The first major radiation was among sauropodomorphs, early relatives of long-necked sauropods like Brachiosaurus. Still modest in size, they filled the large herbivore role. Their fermentation-based digestion handled conifer and fern-dominated flora better than Dicynodont jaws, allowing steady growth. By the Triasic's end, some exceeded 5 meters. Carnivorous dinosaurs followed. With new herbivores to hunt, theropods, the lineage that would later produce Tyrannosaurus and birds, diversified. They grew larger and more specialized, with the fossil record showing clear increases in size and ecological roles. Why dinosaurs? The debate continues, but several advantages stand out. Upright limbs made them energy efficient and fast. Rapid growth allowed them to reach maturity quickly. Their generalist diets and adaptability gave them an edge in a recovering world. Dinosaurs were not alone in their success. Expanded rivers, lakes, and swamps provided ideal habitat for early crocodilian ancestors, which diversified rapidly. Turtles and lizards also appeared during or shortly after the CPE, exploiting new niches. Among synapsids, the large Dicynodonts vanished, but small carnivorous and omnivorous cynodonts endured. During the CPE, the first mammalomorphs, tiny, likely nocturnal insect-eating creatures, emerged. These shrew-sized survivors of
Yeah, this is like not super related, but just this just looks to me like a haired naked mole rat, which I guess would be a clothed mole rat. It's kind of like the vibes this guy gives me.
and were our ancestors. The plant world.
Okay, so it's like a mammal.
Conifers, once minor players, became the dominant trees across Pangaea. With deep roots and tolerance for variable conditions, they thrived where seed ferns faltered. The great forests of the Jurassic and Cretaceous, the age of dinosaurs, were conifer forests. The story of the CPE was not discovered by one person or in one place. It was assembled, piece by piece, over decades, by geologists, paleontologists, and geochemists working on different continents. The first clues came from stratigraphy, the study of rock layers. In the 1970s and 1980s, geologists studying Triassic rocks in Europe noticed something odd. In the middle of the Carnian stage, between layers of red sandstone, typical of arid environments, there was a band of dark shale and coal. The same pattern appeared in China, then North America, then South America.
So one thing that's really important for understanding like Earth's global history is like when you see a layer that is continuous across not just like one area, but is continuous across the geology of like many different areas that are dated to about the same age. That is like a sign that's like, oh wow, there was a global change here that we need to understand.
The layers were deposited at the same time, based on fossil correlations and radiometric dating of volcanic ash vents. This was unusual. Climate shifts are typically regional, not global. Deserts don't turn into swamps everywhere at once, but the rock record suggested exactly that, a synchronized worldwide shift from arid to humid conditions. In the early 1990s, British geologists Michael Sims and Alistair Ruffle formally proposed that this was a distinct climatic event. They called it the Carnian Pluvial episode. Their work synthesized observations from multiple sites and argued that the change was driven by a major perturbation to the global carbon cycle. The link to volcanism came later. Geochemists analyzing carbon isotopes in Carnian rocks found a sharp negative excursion, a sudden shift in the ratio of light to heavy carbon isotopes. This signature matched the isotopic composition of volcanic carbon dioxide. The timing aligned with the large igneous province, a massive basaltic eruption on the western margin of Pangaea. The connection was clear. Volcanism drove greenhouse warming, which drove increased rainfall. Paleontologists added the biological context. By carefully documenting the fossils found in each rock layer, they could track which species disappeared and which appeared. Dicynodonts vanished. Dinosaurs multiplied. The turnover was dramatic and coincided exactly with the CPE layers. Palynology, the study of fossilized pollen and spores, provided the botanical evidence. Pollen from seed ferns dominated pre-CPE samples. Conifer pollen and fern spores dominated post-CPE samples. The floral revolution was quantifiable. Even trace elements played a role. Elevated mercury levels in CPE rocks provided additional evidence of volcanic activity, since mercury is released during eruptions and deposited globally. Each line of evidence, on its own, might be ambiguous. Together, they form a coherent picture. The CPE is one of the best documented rapid climate events.
Okay, I don't know. Oh, I don't know if I would say it's one of the best documented. There are a lot of the Cenozoic hyperthermals, I would say, are probably like way more documented, or maybe even the banded iron formation. But maybe I don't know specifically about this, but I am curious.
Earth's history. It's a case study in how science reconstructs the deep past, not through speculation, but through the patient accumulation of data from multiple independent sources. The Carnian pluvial episode lasted roughly 2 million years. Then it stopped. The Wrangellia eruptions ended. CO2 levels, still elevated compared to pre-CPE conditions, stabilized.
Yeah, so one thing that I am curious about with this is like the way he's covering this with like the 2 million years versus like the 10,000 years he mentioned earlier. There seems to be like a time gap, okay, did this start at like, in the period of like 10,000 years, or did it like slowly ramp up over 2 million years? Because I feel like the 2 million years is like more reasonable. So I just like, I feel like this guy should have communicated this a little bit clearer, or maybe I'm just misunderstanding something.
The greenhouse effect weakened, rainfall decreased. The world dried out again, not to the same degree as before, but enough that deserts returned to some regions and seasonal rivers re-emerged. But the world those rains left behind was unrecognizable. The ecosystems that had dominated Pangaea for tens of millions of years were gone. Dicynodonts, rhynchosaurs, edosaurs, the fauna of the dry world, were extinct or irrelevant. In their place, dinosaurs. By the end of the Triassic, 30 million years after the CPE, dinosaurs were the dominant large animals on every continent. They would remain so for the next 150 million years.
Actually, wait, hold up.
Edosaur.
When is this supposed to be? Because like one thing that that's like okay, there's like there is a lot wrong with this image, because yeah, I think this is just dated. Whatever, that's fine.
The dry world,
Okay.
were extinct or irrelevant. In their place, dinosaurs. By the end of the Triassic, 30 million years after the CPE, dinosaurs were the dominant large animals on every continent. They would remain so for the next 150 million years. The CPE is a reminder that Earth's systems are interconnected. Volcanism affects the atmosphere. The atmosphere affects the oceans. The oceans affect rainfall. Rainfall affects ecosystems. Ecosystems affect evolution.
Yeah, I do like how he's wrapping this up here, because the Earth as a system is just like a huge series of cycles that interlock with each other. And yeah, the amount of rainfall that you get does impact the sea level. And at least locally, on shorter time periods. But the sea level does impact rainfall. And the temperature of the Earth impacts how high the water level is, which impacts what areas can be eroded, which impacts the rate at which carbon dioxide can be sequestered back into the environment. So there are a ton of just mechanisms that loop back into themselves and create the controls and the reason why we have a consistent climate at all. It's not like Mercury, where the part that's facing towards the sun is like 200 degrees, or maybe even hotter, like 300, 400. I'm thinking of Fahrenheit, but it's probably hotter than that. And then on the other side, it's like negative 200 degrees Fahrenheit. At least most of our Earth stays between, like negative 20 degrees Fahrenheit to like about like 120 degrees. This is a relatively narrow band, especially compared to places like Mercury or like Venus.
A volcanic eruption in one region
Or
can,
the
through a
moon,
cascade
I'll
of
say, not
feedbacks,
Venus.
restructure life across the entire planet. It's also a
This.
reminder that specialization is a double-edged strategy. The Dicynodonts were spectacularly successful until the rules changed. Their evolutionary investment in a specific food source and climate became a liability when that climate disappeared. Generalists, less efficient in stable conditions, survived disruptions better. The dinosaurs, unspecialized and adaptable, inherited a planet by default. The CPE didn't just clear the stage for dinosaurs, it set the trajectory for the rest of the Mesozoic era. The conifer forests that rose during the episode became the dominant vegetation for the next 100 million years. The first mammals, appearing during the chaos, stayed small and marginal for the entire age of dinosaurs, waiting for their own opportunity. The crocodilians and turtles that diversified during the Cretaceous period are still with us. If the Rangelia eruptions had never happened, if that particular piece of the Earth's crust had remained stable, would dinosaurs have ever dominated? The question is unanswerable, but worth asking. Evolution doesn't follow a script. It improvises in the wreckage. The CPE was a catastrophe for some, an opportunity for others. The 2 million years of rain that drowned the old world created a new one. The dinosaurs didn't conquer the Earth. They walked onto a stage that catastrophe had cleared.